In this video, we're going to be discussing motion problems, which is out of section 3.3. When we talk about motion problems, we're usually talking about planes, trains, cars, anything that moves. So the formula we'll be looking at is distance is equal to rate times time. That is our basic formula. So distance equals rate times the time. This is a formula you already know. For example, if your rate is 60 miles per hour and you drive for 2 hours, then you know you've traveled a distance of 120 miles. So this is something we're sort of familiar with, but you may not be familiar with writing it in this form. We usually call it the D equals RT formula. Now you can solve for either R or T, so this would give us two different versions of the formula. If I divide both sides by T, then I would be able to write this as R is equal to distance divided by time, and that would give me the rate or the speed or velocity. But you could also solve for time, and then you would write that time is equal to the distance divided by your rate of travel or your velocity or speed. We can use any of these formulas to solve for one of the unknown variables. However, these problems are not all set up the same way. There are many different ways to set them up, and we need to find out how they're set up. So let's take a look at the first one. We're going to be taking a look at problem number 46. Let's read the problem together. It says 2 cars leave Salt Lake City traveling in opposite directions. One car travels at a speed of 80 kilometers per hour and the other at 96 kilometers per hour. In how many hours will they be 528 kilometers apart? So again, when you're reading these problems, the first thing you want to do is read the entire word problem through from beginning to end. You're not trying to remember all the specific information. You're not trying to come up with formulas. All you're trying to figure out is what kind of problem is this. When you read this one, you read about cars and speeds and hours. That tells you that this is a distance equals rate times time problem, but it also tells you that it's not, for example, an interest problem. There's no banking, there's no money. It doesn't have anything to do with area or volume. So the formula you will need here is the one that relates distance, rate, and time. Then you go back to the beginning of the problem statement and you read it using the parts of speech, the subject phrase, the verb phrase, prepositional phrases, subordinate clauses, punctuation marks, looking for clues as to how to translate the words into mathematics. And if you're not good at knowing all the different parts of speech, then what you need to do is basically read every 2 to 3 words, stop and think whether you should write down some information or draw a picture to represent what's happening in the problem. So let's do that now. Starting again at the beginning, we read, 2 cars leave Salt Lake City. When I pause there, I know I'm going to need to write down something to represent the 2 cars, but I don't know what directions they're traveling in yet. The next phrase gives us that, traveling in opposite directions. So I stop there and I'll go to the picture and I might put down something that represents Salt Lake City. So in my case, I wrote down SLC for Salt Lake City. If the cars are traveling in opposite directions, then I can show that by showing one arrow to the right and another arrow to the left. So far, that's all I know. The 2 cars leave the city traveling in opposite directions. Next sentence. 1 car travels at a speed of 80 kilometers per hour. I need to stop and write that down somewhere. So I'm going to let the car on the right be the one that's traveling at a speed of 80 kilometers per hour. To decide whether it's distance, rate, or time, I can look at the units. Kilometers per hour would be distance divided by time, so that has to be the rate. So this car is traveling at a rate equal to 80 kilometers per hour. I don't want to try to remember the information, so I'm going to write it down so I don't need to come back to the words again. Then I continue reading the problem. And the other at 96 kilometers per hour. Now I have another piece of information that the other car is traveling faster at 96 kilometers per hour. I write that piece of information down on the other side of Salt Lake City to represent how fast that car is moving. I still don't know what it is I'm trying to find. Usually the information about what you're looking for is in the last sentence or the second to the last sentence in the word problem. We only have one sentence left. Let's see what it is we're looking for. In how many hours? So I can stop right there. In how many hours already tells me what they're looking for. They want to know the number of hours. So when I'm done, I should be able to answer the question and fill in the blank that time is equal to a certain number of hours. It's also important to note that it's hours and not minutes or days, because sometimes the information might be given in minutes, but they want the answer in hours, or they give the information in hours, but they want the answer to be in minutes. Then you'd have to convert from one to the other. So let's continue with the last sentence. In how many hours will they, got it, be 528 kilometers apart? So basically that means at some later point in time, if one car is reached here and the other car is reached there, they want to know what time it takes for the distance between the two to be 528 kilometers apart. Now that means that both cars have driven less than 528 kilometers apart, because that's the total distance apart that they are. One drove in one direction, the other car drove in the opposite direction. So this car that's traveling 80 kilometers per hour drove part of the 528 kilometers, and the other car drove the rest of the 528 kilometers. But we're looking for the time it takes to do that. So since 528 is a distance, and because I know that this is the total distance between them, total means add. Now you'll notice that the word problem itself didn't have the word total in it. That's something I have to draw out of my understanding of the problem and from the picture that I have. Because I can see here that this distance D1 and this distance D2, if I add D1 and D2, that should give me 528 kilometers. So I can write down D1 plus D2 equals 528 kilometers. Now what is the distance that the car traveling 96 kilometers per hour has driven? If you look at the formulas up here, it says D equals RT. I don't know the time because I don't know how long they've been traveling. That, in fact, is what I'm looking for. So if I let T be the time they've both been traveling, I can represent car 1's distance, D1, with RT. That would be 96T. That's the formula for distance traveled. The second car is traveling at a rate of 80 kilometers per hour. It travels for T hours, and that would give its distance as 80 kilometers times T hours. Again, if I pretended it was 2 hours, then I would know it had traveled 160 kilometers. That would be 80 kilometers per hour times 2 hours. So when I multiply them together and add them up, I should get the total distance, which would be 528 kilometers. When I get this equation written down, one thing you'll notice is this equation, the second one, only has one variable in it, and that's time. Since these are both t terms, then I can add them together. I have 96t plus 80t, and that should be 176t equals 528 kilometers. Now I need to divide both sides by the 176. Keep in mind that the 176 is actually kilometers per hour because those were rates. So now I have kilometers per hour times time, and I'm going to divide by my 176. So I end up with t equal to 528 kilometers divided by 176. And when you divide by kilometers per hour, the hour will get flipped up to the numerator. Remember that the bottom of the bottom is actually on the top. So the kilometers will cancel, but when you divide by a fraction, the denominator of the bottom fraction becomes the numerator. So what is 528 divided by 176? You can either use your calculator or do the long division by yourself, but you should end up with 3 hours as your answer. That's the end of problem 46. Now let's take another look at a different problem that would be set up slightly differently. This one is a boating problem and is problem number 48. You'll see up here at the top that I've written that we're working on problem 48 out of 3.3, and I've rewritten the three formulas for the distance, rate, time situation. Now let's read the problem. Chen's motorboat took 3 hours to make a trip downstream with a 6 mile/hour current. The return trip against the same current took 5 hours. Find the speed of the boat in still water. Again, the first time I read it, I'm not trying to write down the information. I'm not trying to remember anything. I'm just trying to figure out what kinds of formulas might be useful in solving the problem. The word motorboat or boat tells me that I have something traveling. That tells me it's probably a distance, rate, time formula. Then when it talks about hours and miles per hour, that confirms that I'm looking at a distance, rate, time problem. Now that I know that, let's go back and break it up into the parts of speech about every 2 to 3 words and see what we need to write down. When you're doing a word problem, the picture is really the most important part. If the picture is right, it's much easier to set up the problem. If the picture is wrong, then the problem will almost certainly be solved wrongly. Let's read. Chen's motorboat. Okay, the first thing I'm going to do is I'm going to draw a boat. Now I can't draw, so my boats are pretty pathetic, but I have a boat, so I'm going to represent the boat. Chen's motorboat took 3 hours. So I know I'm going to need to write down 3 hours, but I don't know what the 3 hours represents yet, so I'll wait. To make a trip downstream. Okay, now I have something I can draw. When they say downstream, they're usually talking about a river, something that has current in it. So I'm going to go ahead and draw a picture of a river. And if the water is flowing this way to the right, then that would be downstream. Upstream would be flowing against the water. So downstream, it took 3 hours. So I can write time to go downstream would be 3 hours. It also said, if you continue reading, that it made the trip downstream with a 6 mile/hour current. Now I need to represent this. I might even put a lowercase d below the t to represent this is the time it took to go downstream, 3 hours, and the speed of the water, and I can write rate of water, was equal to 6 miles/hour. Now, you can write mph like it says in the car, but you can also represent that mathematically by 6 miles divided by hours. The word per means divided by, so 6 miles/hour becomes a fraction, 6 miles divided by 1 hour. Next sentence. The return trip, okay, against the same current. So the boat was here, traveled downstream, then it turned around and went upstream against the current. So that trip took 5 hours. So then I can write down on the opposite side of the river that the time to go upstream was 5 hours. Last sentence says, find the speed. Okay, so I'm looking for speed, so that would be rate. Rate equals something of the boat in still water. So what do they mean by the rate of the boat in still water? So when you're talking about still water, you're talking about how fast can the boat go just by itself. Think about trying to swim in a river. If you go with the current, you can go really, really fast. On the other hand, if you're trying to swim upstream, you're against the current and it really can slow you down. So the rate of the boat in still water means if there was no current of the river, how fast could the boat go? If the river wasn't helping it go faster downstream or slowing it down going upstream, how fast would it grow? So let's see what we have now in our picture. We've read through all the words. All the information is down on our picture. What do we notice about the picture that would help us set up the problem? This one is not like the last one where the two distances added together. In fact, if I think about the distance, I have one boat going downstream, stopping down here, then turning around and going right back to where it started. In other words, the trip downstream and the trip upstream were the same distance. So I can write that down in words, that the distance downstream has to be equal to the distance upstream. And if I think about that, that should let me maybe come up with some formulas. What would the distance going downstream be? Looking at my formulas for distance, rate, time, I know distance is rate times time. And when I'm going downstream, the rate was 6 miles per hour for the current and 3 miles for the total travel time. But how fast was the boat moving? The current's moving 6 miles per hour, but that's not what the boat is doing. Let's say that the boat under its own speed could go 10 miles per hour. If the boat can go 10 miles per hour in still water, then with a 6 mile per hour current, wouldn't it be able to go 16 miles per hour? Because the boat itself can go 10, plus the current is pushing it to go faster because it's going with the current, and that would make it go 16. So when I write a formula for the distance downstream, I need to take into account that there are two rates involved. The rate of the boat itself, which I can call R, and the rate of the water, which is either pushing it downstream or going against it going upstream. Going downstream, that would be 6 miles per hour. So the rate going downstream is the rate of the boat in still water plus the current. And then when I multiply by time, I will end up with the distance that it travels downstream in those 3 hours. The return trip means it starts and comes back to where it started. So this has to be equal. The distance downstream equals the distance upstream. At this point, how would I represent the rate when it goes upstream? Well, if the boat's not capable of traveling faster than the current, then the boat will not go upstream. If the boat could only go 4 miles per hour, but the current's 6 miles per hour, then that means the boat will go downstream regardless at a 2 mile per hour rate. In other words, they're working against each other. So I know for the boat to go upstream, that the boat has to travel faster than the current. So it's got to be more than 6 miles per hour or it couldn't even go against the current. So in this case, the rate of the boat going upstream will subtract the rate of the current, which is going downstream. So now I have R minus 6, and the time it took to make that return trip is 5, which is what we would expect. The current is slowing down the boat when it goes upstream, so it should take longer to make that trip. Once I have the equation written down, you can see that I only have one unknown, and that's R. So the next thing we need to do is multiply it out. Now, if it bothers you to have the 3 at the back, remember that multiplication is commutative, so you can reverse the order, and you can rewrite this as 3 times R plus 6 equals 5 times R minus 6. Now we'll apply the distributive property, and remember, if you see these arrows, it means you failed to distribute the outside factor over the addition or the subtraction correctly. This would give me 3R plus 18 equals 5R minus 30. Since 3R is smaller than 5R, I'll move the 3R to the right side by subtracting. That means the constants need to move to the left side to isolate R on the right. So I'll add the 30 to both sides. And that would give me 48 on the left equal to 2R on the right. When I divide both sides by 2, I come up with the final result that this is actually a quite fast boat. This boat is traveling 24 miles per hour. That's the end of this video, which is talking about motion problems. This will not be our last time to work with motion problems. They'll be coming back again in a later section. Don't forget when you give the answer to be sure to affix the proper units. I got the answer 24, I know it's rate, and I can either write it as mph for miles per hour, or I can write it in the fraction form of miles divided by hours. They represent the same thing. In the next video, we will be talking about some business applications and word problems related to those.